I'd like now to continue to talk about something I started referring to last time, which is object-oriented development and its particular vulnerabilities, ladies and gentlemen. And I thought that I had, yes, here it is, my tablet, just to keep track of time here. Okay. Object-oriented systems. I had noted last time that there were early heady hopes for object-oriented development. The idea was through reuse, we'd be able to lower the amount of new code we have to write for every new product, and thereby lower the amount of bugs that are incorporated in that project. Okay, and to a degree that's true. You make use of a lot of libraries that you build on top of. Those in the room are building on top. They're standing on the shoulders of giants who are providing lots of services. So some of that has come about, but also object-oriented systems have introduced some pretty distinctive risks and vulnerabilities and barriers to effective testing. Okay, and I noted last time in words some of the particular vulnerabilities, but I'd like to go through some specifics about barriers here, and I'm going to go through a set of about 4 different sort of major challenges for quality assurance with object-oriented systems and recommendations for how you can deal with these things. So our first challenge has to do with encapsulation. Encapsulation, as I think someone said last time, has to do with separation of public and private interfaces. Now, I should know, this is a point that came up in some of the marking and in discussions with some groups. And I want to be clear. When I use the term interface, this term by itself, left in isolation, it's a bit ambiguous. Okay, I could talk about the interface to the program. I was, interacting with the interface, and there it might mean like a GUI interface, a graphical user interface, or for that matter, a textual interface. Right. The point is there's some sort of, maybe it's a console. There's some sort of user interface, right? But another use of interface that I'll do has to do with this dichotomy between the interface and the implementation. And here, we're basically talking about the contract or the specification, the contract associated with a piece of the system. So I'll talk about the interface to this area of the system, and I'm basically talking about the API and the promises that it makes, hence contract. What promises does this API make, this class? It has certain methods, and this is one of the reasons it's important to not just be setters and getters, but it has operations or services it offers that require certain things as input. They have certain preconditions, okay? And when I talk about an interface here, I'm talking about the API. It's this I there, application programming interface, okay? And I'm distinguishing that from the actual implementation of it. I'm saying we're talking about the interface, the contract itself, so that people who use these services know what to expect, know what's guaranteed, okay? And object-oriented techniques in general distinguish the implementation from the interface. And in fact, in C++, we do that all the time, right? We have a .h file that describes the interface to a class and a .cpp file that provides the implementation. But particularly in recent years with design by contract and use of languages that are somewhat higher level, we have these constructs in the form of what are called interfaces in Java, right? The interface, you declare an interface, or abstract classes, which provide only partial implementation. These define interfaces which are then implemented in a number of different ways. So when I'm talking about separating interface from implementation, I'm talking about separating the contracts, the promises being made, from how it's accomplished, the implementation. All the details of how it happens. Because, and if you take 470, you'll you'll recall, or you will see, that it's very important that we be able to achieve abstraction in the form of having many particular implementations that could satisfy the same interface. By separating the two, we can evolve the implementation separately from the contracts. The contract will stay constant, but we make the implementation more efficient or clearer or require less space or be more reliable or what have you. And that's very important. The rest of the code doesn't have to change because it's just going through the interface. Okay? Okay. Ladies and gentlemen, so there's many benefits for doing this. And in object-oriented programming, we try to separate out the interface in part by hiding the implementation details. Well, in general, that's what you do. And what this means is that users of an instance of a class cannot access the internals of that class directly. Give me a concrete sense. What do I mean by I can't access the internals of a class? What might I make private to a class? Very commonly in object-oriented systems.
A variable.
A variable, yeah, an instance variable. A field of that class. You'll often be very hesitant to make that public. Why is that? Why might you make it private? What's the matter with having it be public? Then you don't need a getter and a setter for it. Just make it be public. What's the matter with that? What's the vulnerability?
It could be changed in ways it shouldn't be changed.
It can be changed. I love it. I love it. Thank you. Thank you. So it can be changed in ways that would not be legal. For example, it could be assigned to an illegal value, right? It has to be positive, and someone just goes and assigns it to -1 or something like that. Suddenly your assumptions of that class are broken. It's assigned to null, right? Another vulnerability is that if you go around assigning to this variable, the class is not aware it's been changed. It might have to recalculate certain internal data structures every time that updates, and it doesn't even know it's been updated. It hasn't woken up to the fact that it's been changed. Another vulnerability is you don't want someone knowing all about the internals of this class, because then the person who creates the class can't really evolve those internals. They can't turn that variable of one type into a variable of another type, because there's all this code counting on it. It's counting on this variable being available and of a certain type. So it really limits the evolution of that class. You can't turn that variable instead into a function which just returns appropriate values through calculating it rather than through a variable, because other code is counting on that. So ladies and gentlemen, generally we try to hide the internal details. We make things private, okay? And that offers lots of benefits. Modularity, separation of concerns, greater user clarity on what's promised for the users of that class, and the flexibility for the creator in evolving the implementation. We can develop our code base separately, not in as much of an entangled fashion. Okay, now the risk here is that this encapsulation can inhibit testing. Because now your test script, your test harness that's running your system through tests, can't directly reach in and check whether an internal variable of this instance looks reasonable. It can't directly sort of look internally and see if the data structure is in a sane state. It can't ask that directly because it doesn't have access to those things. They're private fields. So how do you deal with this? You provide, ladies and gentlemen, a testing interface, test hooks. You provide methods which aren't used by normal people using the class, but which are used for testing. You ask, is the data structure sane? Are the invariants of the class being met? Is the class in a state that abides by its specification? In other words, you provide mechanisms for testing the internal state of a class just for the sake of testing. So this has to do with testability. Maybe some of these test hooks, which are exposed to a different interface, maybe they return values that the test driver can use to see if the operations worked or not. So, ladies and gentlemen, if you want to test your program well, it can be hard to reach into other classes and see what's going on. So you often want those classes to have some methods provided for the sake of testability. And that, ladies and gentlemen, was another big gap in the deliverables for IB2. I didn't see a lot of discussion of testability. How are we going to make our system be able to be tested effectively? In order to do that, you'll often want to provide extra methods. Okay? You might want to provide test code as part of the class subclass definition. So if you're using JUnit or NUnit or any other similar frameworks, many of them sort of bundle together the test code with the class code. So you have certain test methods intermixed with other methods. And that partly deals with this encapsulation, the fact that we can't have an all-knowing test harness that drives the system and reads and checks everything. So instead, you build test code into the system. Okay? And then, clear statement and checking of class contracts can be really valuable for checking of preconditions, postconditions. Have the class check itself whenever it undergoes an update. Am I still sane? Am I still in a good state? Have somehow a null pointer been inserted into the hash table as a key or a value or what have you? Are there duplicates suddenly in the keys, etc.? Put in place assertions, because remember, ladies and gentlemen, don't be afraid if an assertion takes a while to run. Typically that's not a problem, because assertions at runtime, when the user is using the system, assertions go away. You turn off assertions. You actually tell the Java compiler, turn them off now, in many cases. And as a result, you can actually do it on a per module basis. As a result, if you have assertions in your program that are doing pretty heavyweight things, checking this against that, having this simple version of the algorithm checked against a more sophisticated one, it's not a big deal. You can turn them off on a per module basis. Okay, so that's one set of things. Encapsulation, ladies and gentlemen, the fact that we can't reach inside an instance willy-nilly puts in place a need for certain types of test conventions or disciplines, including test hooks, incorporating test code into a class rather than external to it, and a clear statement of class contracts. Okay, now the next couple vulnerabilities have to do with polymorphism and subtyping. And those who are in 470 now will find this comfortable material. We're not going to go into it like we did in 470. But when you have a type hierarchy, as we do in Java, we can use polymorphism in very, very effective ways. So we can pass around a set, for example, as a collection, right? Pass anything that expects a collection could deal with a set. Anything that expects an iterable could be given a set or a queue or a list. What is the benefit of this to us? Give me one benefit.
Allows you to compare sets and queues and lists and stuff.
Okay, so we can sometimes have common mechanisms that will operate on all of these. And really what we're talking about is we can reuse code. Code could be written, instead of having to be written separately to deal with lists and to deal with queues and to deal with sets. There's quite a bit of code that can just be written to deal with an iterable. Doesn't care whether it's a list, a queue, or a set. And you could reuse that code again and again and again for each of these things. Not only that, but you might introduce your own collection. And suddenly this code that was written long before you thought of creating your own collection can be used by your code. It can use your instances, okay? So that's good stuff. You can reuse code. But part of that comes with that opportunity, with that benefit, comes, ladies and gentlemen, great responsibility, okay? And it's particularly this ability to decouple the actual type, the fact that secretly, this is a linked hash set, from its apparent type. It just looks like an iterable, or it looks like a collection. The fact that we're separating those out means that we have to protect against a user's understanding, as secured from the description of an iterable, from being violated by one of these classes down here, enum set or hash set. The fact that I can pass around a linked hash set as a collection or a priority queue as a collection means they have to abide by certain rules that are to be expected for any collection. Okay? So polymorphism has to do with separating out this fact that, you know, I actually have a certain apparent type collection, and it's different from my actual type, the concrete type, linked hash set or priority queue. This is the actual type I have, but all I know is that it's a collection. Right? You pass me a collection. That's all I know. Maybe secretly it's a priority queue. Maybe secretly it's a linked hash set. Maybe secretly it's a tree set. Maybe it's secretly something that you defined. But all I know is that it's a collection. Okay? So many benefits to this, particularly for code reuse and for code reuse. The risk here is fraudulent subtypes. So we might have one of these subtypes down here that masquerade like a collection, but they actually don't abide by the rules of collections as someone looking at the collection contract will conclude. If someone who wrote their code against a collection, all they're operating off is knowing how collections work, as seen by the collection interface, the collection contract, ladies and gentlemen. They're counting on this contract being the case. And if something is passed along as if it's a collection, they have no way of knowing what this thing is directly for the most case, or they don't know what it is. Then they're going to be assuming that it's a standard collection and abides by all the rules of collection. So anything that they can assume, given it's a collection, should be able to be assumed, should be able to be the case, should be able to be proven for any of these ones down here. Okay? So if from a collections interface you assume certain properties, those properties should hold for these guys down here. Okay? I go into this much more in 470, as many of you know. And the risk is, if you don't adhere to it, if one of these classes down here, say a linked hash set, violates the assumptions about collection, then the code that's written against assuming a collection will break. And the principle here is called Liskov substitution principle for Barbara Liskov. And basically anything that's provable about the super type needs to hold true for the actual subtype. Okay? And the way we work to guarantee that is providing clear specifications, if possible. Okay? And we want the specifications for the subtype to be compatible with the supertype. Now, you can go see videos of me talking just about this, and some of you have seen me in person talking just about this. The deal here is when we test object-oriented code. Now, I'm particularly thinking about those using Swift, for example. Swift, which does have subclassing supported. You're going to have subtyping going on. You're going to have cases where you pass something in as if it's an X, even though it's actually a Y. And it needs to abide by the assumptions of X. So what you should be doing is, ladies and gentlemen, is putting in place some guards to make sure this Liskov substitution principle hasn't been violated, particularly those of you using object-oriented features of a language, including polymorphism. So use assertions. I want to see use of this assert. JavaScript has assert. Python has assert. Many modern languages incorporate into the language, if not the library. Okay? So please use assertions to check the contracts associated with class. If you have an instance variable that has to be non-negative, like it's a index into an array, check that it's non-negative every time it's modified. Check that it ends up being non-negative. Okay? Every time it changes, make sure it abides by the constraints. And you should be testing subclasses against specifications, if possible, for superclasses. In other words, what are the superclasses assuming about certain things. Maybe the superclass assumes the data structure has no duplicates. You'll want to check those for the subclass. Okay, and then you'll perform particularly heavy testing in code, making use of polymorphism. Okay, and you know, if you have explicit casts against types, if you're explicitly casting to a type, you're going to want to make sure that indeed those things are of that type. Okay, and that's because errors that would normally occur at compile time will be occurring at runtime. You're going to want to make sure that that cast is always safe by making sure that the things being casted when they're first being initialized, that they're of the right type. Okay, so Liskov substitution principle. The issue here is that the promises being adhered to by the subtypes may not adhere to the promises that are being expected for the supertype. If you pass something in as if it's a collection, you need to live by the rules of collections in terms of what the guarantees are. If someone could come away with an understanding of those guarantees from looking at the code, you need to abide by them. So, ladies and gentlemen, that's risk 2, fraudulent subtypes. I want to talk about another risk that's related, which has to do with subclassing. Okay? So subclassing involves subtyping. If I make one class a subclass of another, such as Java extends, then I can pass it around as if it's that superclass. Right? Comes along with it. Comes along with that subtyping. But something else is involved. Can you folks give me an example where something could be a subtype of another thing, but it's not a subclass of that thing? What does subclassing give you beyond subtyping? Subtyping lets you pass it around as if it's an X. What construct in Java can you have where there's no implementation involved? You implement it, and you can pass it around as if it's one of those. What construct?
Abstract.
Okay, so an abstract class. Yep. It has no implementation yet. Okay, that's good. But an abstract class often has some implementation, right?
Interface.
An interface. So if I say class A implements some interface I, there's no subclassing going on. I'm actually not reusing the implementation of I. There is no implementation of an interface. It's just a statement of a contract of what services are provided, and hopefully, with comments, what the guarantees are. Okay? So here, there's subtyping going on, but no subclassing. Okay? I can pass an instance of A around as if it's an I, and it will be treated as an I, but there's no subtyping. Okay? Oh, so there's no subclassing going on. It's where you have class B extends class C. Can I pass a B as if it's a C? Can I pass around a B as if it's a C here? No. I would say you could. You should be able to pass around an instance of B as if it's a C. So I have a here. We'll go back to this. So if we have a linked hash set that is a subclass, it extends hash set, I would submit to you, in no uncertain terms, that we could pass around a linked hash set as if it's a hash set. Anything that expects a hash set, I could give it a linked hash set. So it actually does involve polymorphism. There's subtyping involved here. But there's also something else going on. What is that other thing that's going on that's not going on for this case here? This one does what? It reuses the implementation of C. It actually uses the it takes the implementation of C, and it may modify it by overriding certain methods, right? But it reuses that implementation. Now that has big implications. I mean, up here with subtyping, we're just talking about a situation where A has to adhere to the promises being made by the interface. The promises being made by A. And in fact, its implementations of them need to adhere to these promises. But here, we actually have subtyping, but also subclassing. Okay, it's actually reuse of implementation. And there's a word for it that's often used, which is inheritance. So with this inheritance, B is actually making use of the implementation of C. It's making use of how the methods are implemented, the fields that are present, etc. So that's what you're getting with this relationship. What that you're not getting with, say, set being a subtype of collection. This thing is making a statement about promises. The promises made by set need to be consistent with the promises made by collection. This relationship here is talking about implementation reuse as well. Not only does linked hash set have to be consistent in the promises with that of hash set, because it can be passed around as one, but linked hash set's implementation needs to be compatible. Okay. Now the risk here, ladies and gentlemen, is that it's very easy to have a subclass break the implementation of the superclass. Okay. One way, it violates the Liskov substitution principle. The promises it makes are different and incompatible. You can't assume anything. If you can't assume, let me put it baldly, if you can't assume something for the subclass that you can for the superclass, something's broken. Because it can masquerade as the superclass. And someone who only knows about the superclass can be given one of the subclass instances without knowing that that class even exists. It's passed in through a different area of the program or what have you. And as a result, they're counting only on the features of the superclass. They might have written their code against writer long before you created your subclass of writer. And their code should not break just because you pass in your own subclass of writer. Okay? So one issue is it can break the promises. But another issue is that the implementation of the subclass can fail to capture the intended behavior. Okay? And it may break when the superclass is modified. Okay? So the issue here is one that folks in 470 will have seen. But I want you to be aware of it so you can test against it. Okay? Here we go. So I want you to think this through. Here's a little puzzle for you. Okay? Okay, so here on the left, we have a superclass. Okay? We have a superclass, which is hash set. And here on the right, we have an instrumented hash set. And our goal is to create a subclass of hash set that basically records the number of times things have been added into this class. Okay? Otherwise, it's a hash set. But it's also recording this extra bit of implementation, extra bit of information, namely the number of times things have been added. So we want to keep track of the number of times things have been added. Okay, here's the superclass, add all, and get count. And here's our subclass. Okay, here are some constructors for the subclass. They just delegate to the appropriate constructors. Okay, by the way, an occasional thing you'll find broken in subclasses is you forget to initialize the superclass. Bad things can happen with a capital B. If that's the case, that's a vulnerability you're going to want to test for. Make sure the superclass is in a sane state, because if you fail to initialize its superclass, the superclass, it may be in a whacked out state with respect to its situation. But ladies and gentlemen, you'll notice here we have an add and an add all method, and then this get add count. So remember, the goal of this subclass is to keep track, is to maintain a hash set, but to keep track of the number of things that have been added. Let me ask you, is this implementation that's here going to work? Why not? Yes or no?
If you try to add something and it fails, it'll still increment the add count.
Okay, so there's some issues with failure, although presumably that would normally be handled with, it's a good idea, but I don't see any declaration associated with exceptions to be thrown, which is normally how they'd be thrown.
Right.
So,
It returns a Boolean. That's probably the, isn't it?
sorry?
It returns a Boolean.
It does return a Boolean, but that's this actually also returns, okay, I should have made that clear. This actually will return a Boolean. So these are good ideas, and you'd want to think about failure conditions. It's true, like if this were null, you know, maybe this fails, right? And this increments. Maybe that's what you were thinking of,
Yeah.
and that would be good. That's a good one. I like that. We should really put a specification in here, make it clear. But there's another problem here. What is that problem? I would say that what's going on here is risky. It's risky because it's not under your control whether it's correct or not. What's the problem? Yes?
Yeah. The easiest implementation of add all is just calling add.
Exactly. So maybe the way add all, notice these guys, for add, it just delegates to add here after incrementing this count. Add all, it just adds to the count, and then it calls to add all in this superclass, right? So it's just mostly delegating over, keeping track of some bookkeeping information. That's how it's operating, right? Now the problem is, and Bert identified it there, the risk here is that whether this is correct or not depends. What does it depend on? Bert put his finger on it. It depends on whether or not add all in the superclass, to do its work, it calls add. Okay, let's suppose add all in the superclass does not call add. It just goes through and manually adds things in without calling off to its own add. Then, indeed, we call add all here. It adds to our count the number of things to be added. We call off to add all. It does its work, and we're home free. But what will happen, ladies and gentlemen? This is really important for understanding superclassing and some of its challenges. What will happen if add all here in the superclass is defined as calling add? If it just in turn goes through and calls add for each item, whose add will be called? So we call add all in subclass. It's secretly a member of the subclass. We call add all on it. It adds to add count, this count of the number of times we've added things. And now it calls off to add all. Add all is going to call add, right? Suppose it does. Whose add will it call? Whose add gets called? In Java, guess whose add gets called? Subclass. This gets called. Now, why is that a problem?
So then you're incrementing twice.
Because then you're incrementing twice. You're counting things twice. You're counting them once here. You're adding in the number of things called, and then you're adding them in here. So now you've got an issue, because at a couple different levels. One issue is this could be broken right now, right? And it could be broken depending on how the code for hash set is implemented. Now, suppose someone were to say, this isn't a big deal, just look at that code for hash set. Why isn't that a solution? Yeah.
It's not specified somewhere, so it might change at any time.
It might change, exactly. Hash set might evolve. If there's no guarantees through the specification, if there's no statement about what's promised, we may be counting on a feature. We do some testing, we find, oh yeah, it double counts when we call add all, so we'll get rid of, this, right? We'll stop doing this. Well, who's to say in the future they won't change add all so it doesn't call add? And that's not under our control. We're writing the subclass. They can evolve the superclass in ways that they see fit, and we don't have control over it. So suddenly, we're in a very precarious position, a fragile position, where the correctness of our code, whether or not it accomplishes our promises in terms of counting the number of times, getting at, it depends on something outside of our control that can be changed at any point. That's bad with a capital B. You don't want interconnectivity between different types of classes, reuse of code, to mean when they tweak their code, your code breaks. That's bad. That is vulnerability. It's not an asset. Yes, you get reuse, but it's broken reuse. By contrast, we don't even know. Well, up front, we don't even know whether or not this is correct. In order to check whether or not this is correct, we could try to go look at that code, but in some cases we won't have access to it, right? I don't know how many of you have spent a long time browsing, java.lang.object, but there's a lot of code out there in the world you have never had a chance to look at because it's not open source. And even if it is open source, it may evolve in a different direction in the future. So what really matters is what Bernd's putting his finger on, which is promises, the contract. What is the contract guaranteed by HashSet? Now, let me ask this. If you weren't implementing a subtype, weren't implementing a subclass, all you were doing was using HashSet. You were just using that as a, you had an instance of HashSet and you were adding things in. Do you need to worry about whether add_all calls add or not? If you're just using instances of HashSet, do you care? No. As long as it does its job, you're fine. Where this vulnerability comes in, ladies and gentlemen, where it really matters whether add_all calls add or not, is when you're implementing a subtype, a subclass of that. That's when you want to know about these implementation details. Does add_all call add or not? If you're just using an instance of type HashSet, you don't need to know whether this calls this or not, as long as it does the job, as long as all you need to know is what it does. But if you're creating a subclass, now you're tied into the implementation. You're reusing the implementation, so you care about the implementation. You care about how this works. And as a result, what you find out is that subclassing, if your code is providing mechanisms for subclassing, you need to provide extra information for people who are going to subclass this class as to what can be assumed about the superclass. So if you're providing a class which is designed for subclassing, in other words, it's not a final class, then, and if you haven't arranged it so the constructors are limited in a way that will prevent subclassing, then you need to be responsible. You need to provide some extra information so that people can reliably use the class. In this case, the information is not sufficient to reliably use this subclass. It's insufficient for task for subclassing. We don't have the required information to know if this will work up front. We don't have the required information to have the guarantee it will work on a continued basis. And hence, it's risky. It's broken. This sort of situation can happen quite a lot with subclassing. You're reusing this code full of goodness, right? But that code, the way you're reusing that code can break dramatically if the code evolves to the superclass. So you want to provide extra information about what calls what, particularly. Particularly, ladies and gentlemen, because add_all, calling add, it'll be calling your add. So suddenly, not only are you reusing its implementation, it's using your implementation. Now, in 470, I talk about ways to handle this at several levels. One way to handle it is to rule out subclassing. Another way to handle it is to write wrapper classes where you don't have this sort of issue. Another way is to have a convention for how you implement methods in the superclass such that you never call a method that can be overridden. The superclass always calls its own internal methods rather than overridable methods. And you could separate it out that way. there's several ways to deal with this, but at the least you should realize this is a vulnerability. So when you are testing classes, ladies and gentlemen, when you are testing subclasses, you're going to want to test to make sure that in the presence of subclassing that you test extra well, is the system working? Because there's these extra vulnerabilities, and when you introduce a new version of the JVM library, you upgrade from Java 6 to Java 7 or 7 to 8, you're going to want to make sure, especially sure, that your code is still working. Okay? You might think it shouldn't matter, but it can matter, particularly when you have that sort of risky inheritance going on. Okay? A related vulnerability is we cannot mock out a subclass, a superclass rather. So this guy here depends, this guy on the right depends on the guy on the left, or the gal on the right and the guy on the left. So there's a dependency here. And normally when we have dependency of one class on another, I've drawn this sort of diagram multiple times, right? We have A depending on B, C, and D. We can use mocking to carve these guys out to test A in isolation. We can mock them out to do thorough unit testing on A. That's not possible in general with superclasses. And as a result, to test the interaction of these, you need code that will particularly test these methods that get overridden, for example. Okay? And this illustrated kind of what's sometimes called the yo-yo problem, where if we look, we call yo-yo because it bounces up and down the inheritance hierarchy. So we call in the subclass, the instrumented hash set, we call add all. So add all. And this is in the subclass. And it calls off to add all in the superclass. So looks like I'll need to erase something. This board is free, so forgive me for those on that side of the room. Okay, so here we have the superclass, and here we have the subclass, and here this is hash set, and the lower one is instrumented hash set. And here we have add all, and add all here calls off to add all here. And if add all calls add, what will happen then is that it will call down to our add. So you have this kind of up and down, the code is executed sometimes in your class, sometimes in the superclass. And as a result, it can be confusing. It can be confusing to developers. And can be confusing about what can be changed when you make an override, what it's changing. So your overrides can break internal functionality of that superclass if you're not careful. So you're going to want to be very careful to perform inspections of subclass code. Please continue to push on the inspections. You can look at my 470 lectures where I talk about ways to provide subclassing interfaces. By interface, I mean contracts. Contracts aimed at supporting subclasses. They're not extra onerous. A lot of it has to do with documenting what variables have to be overridden together or what calls what. But the point is that if you are subclassing a class, you need to know something about the implementation of the superclass that you do not need to use to simply use an instance of that class. Okay? You want to design clearly for subclassing, including providing contracts, these interfaces, or prevent it. How do you prevent subclassing in Java? I mentioned it earlier, but there's one very simple way. I don't know if you folks have used it. Do you know what it is?
Final.
Yeah, you declare a class final. I know you've used final for instance fields, right? That's some constant instance field. It's just a constant that you want to use. And that's all well and good, but you can declare a class final, and it won't be able to be subclass. There's other ways too with constructors that you can do it. But you either want to prevent it or you want to be ready for it. If you're going to provide your class for subclassing, you got to do so in a responsible way that documents extra information. Now there are these tools called class flatteners, which basically document the resulting subclass, what methods come from where, or what are the fields and methods in that subclass. Sometimes it can be helpful to kind of look at a class flattener for a class that's in a deep hierarchy to see the full set of things that are available there. How do we test for subclassing? Well, run the set of tests for subtyping. You want to make sure the Liskov substitution principle hasn't been violated, as we talked about in the first part of the class. But you also want to continue to run unit tests for subclasses, even though you've only changed this. Excuse me. Okay, so you want to run tests for superclass even when we've changed the subclass, and vice versa. So the two are tangled together. You may not have modified the superclass, but the code in it may break as a result of being subclassed in certain places, and you may only have modified, for example, the superclass, and you want to make sure the subclasses are still working properly. Okay. You want to test a mixture of not just superclass in isolation, but the subclasses of it. So if you have something like back here, if you have something like a hash set that you are providing, you don't want to just test it in isolation. You want to test it with linked hash set that depends on it, because the way in which this overrides hash set could break parts of hash set functionality. So you got to be very, very careful to do some testing on that. This initialization of superclasses, common, not an uncommon problem. I found bugs in my code like that, and the basic deal is illustrated with this super. If you forget to call super there, you are forgetting to initialize your superclass. And as a result, variables in the superclass, instance fields, may be uninitialized. That could be really problematic. So make sure when you're doing inspections of code that they're initialized, and do assertions to check the invariants, the things that should be true about those fields for the superclass. If you're providing a superclass, make sure that your preconditions are met, that the class is in a sane state. Because it could be, someone could have forgotten to initialize you when they initialized a subclass that depends on your class. And when you override methods when defining a subclass, you want to retest other superclass and subtest methods. Okay, a final risk, and we'll break, is type parameterization. When I talk about type parameterization for Java, what am I referring to? It goes by a name, begins with G. They're called templates in C++. What are they called in things that are parameterized by type? You could say list of person or list of integer. They're what?
Generics.
Generics, yeah. So if you're defining generics, ladies and gentlemen, you may be using your generics in the program with different type fields. You're using it with an integer field, or you're using it with a person field, or what have you, elsewhere in your program. And when you test the code for the generic, you can't just test it with respect to one of those, but you want to test it with respect to the different ones with which it's used throughout your program. Because the generics, their correctness depends on interaction with the type parameters. So if it has a type parameter C that's given to it, it'll be interacting with C, calling certain things on C. And Java has a big advance over the original versions of C++ and even over earlier Java, in that you can specify constraints here, like C has to implement a certain thing or extend a certain thing. It's just, you can specify rules for what's allowed. But in terms of testing, you're going to want to make sure it works well with the different C's that you use it with throughout the program. Okay, and one thing you can do nicely is use a mock as the type parameter to see if it is operating correctly with mocks, using a mocked up type to see if it's frobbing that the things of appropriate type in the right way. Okay, so type parameterization. Okay, so OO testing challenges. You know, a lot of challenges here. Unit testing is hampered because you call off to a bunch of different types of, you delegate to a bunch of different types of classes sometimes. Use mocking. You know, you need to test this interaction of superclass and subclass. You're going to want to put testing code within classes rather than outside of it because you can't get access to the internals, which are often private. And you know, because of dynamic binding, sometimes what you're calling is not obvious until runtime. You want to use liberal use of assertions. And code reviews, you'll often want to have, if you're reviewing a class that's a subclass of another class that you have also written, you're going to want to have people from both those areas there. The person who wrote the superclass and the person who wrote the subclass. Okay, so code reviews should respond to the needs of OO testing. Okay. Okay, I think that's all we have time for today. Thanks very much. We'll finish up our look over of the code and marking tonight for ID2, and we'll send that along. Okay?